rather than the trial management and how to conduct the study, is actually about how to design it in the first place and how to answer your research question. This is something that you as potential investigators can do, and it's very important to ensure that you adequately answer the question you want and get the results that you desire. So I'm going to start off by making a comparison. These are two studies that you looked at yesterday in the critical appraisal session in evidence-based medicine. And I want you to try and guess which one is which. Two trials. Both trials were comparing interventions, and they found that they had a relative risk reduction of 16%. So the intervention reduced the risk of the outcome measure by 16%. And Hugh's already spoken about the differences between relative risk and absolute risks. One study interpreted that result positively, and one study actually found that there was no difference. So how can this be? Well, let's look in a bit more detail. So the OPTIMIZE trial, which is a study of goal-directed hemodynamic therapy plus a dopexamine algorithm. So goal-directed hemodynamic therapy, for those that don't know, is about how you give intravenous fluid therapy, and about guiding that based on cardiac output and monitoring. So in the OPTIMIZE trial, that was done via a LiDCO cardiac output monitor, but other studies have done it using esophageal Dopplers and such like. So in the OPTIMIZE trial, when they were designing the study, and this was led by Rupert Pearce from Queen Mary, they predicted that they thought the intervention would give an absolute risk reduction of 12.5% or relative risk reduction of 25%, which meant that their sample size predicted was just under 700 patients. But actually, when they came to do the study, they found that actually their relative risk reduction was only 16%, or an absolute reduction in risk of 6.8%. And that meant that when they came to do their significance test, their prospectively planned statistical analysis, their p-value marginally missed out on that 5% threshold at 0.05. The conclusion was that the intervention did not reduce the incidence of the outcome. I'll ask you what you think about that in a minute. This is a survival plot, sort of Kaplan-Meier plot from that trial, and you can see that at the 30-day point, if I use the mouse, 30-day point here, there's a sort of convergence between the two groups, intervention and usual care. And so measuring that outcome at that point, you can see why there might have been a difference in determining between those two groups. If you look out further to, where are we, 180 days, so half a year from surgery, you see there is a divergence between usual care and intervention, but their primary outcome, their prospectively defined primary outcome, was at 30 days. And this trial is actually quite commendable because they didn't change their outcome measure, they stuck with 30 days, which is quite important, as we've discussed. If we look at a different trial, which was another trial that you looked at yesterday, the POISE trial, so this is the preoperative beta blockade trial where they use metoprolol. So this is the largest trial in perioperative medicine that I'm aware of, certainly. So in this trial led by PJ Devereux's group, they did a prospective sample size calculation, and they predicted that they would have, instead of a 12.5% absolute risk reduction, a 1.5% absolute risk reduction. And that equated to a relative risk reduction of 25%. Now, that's an important difference between the two trials. Clearly, in the POISE trial, their outcome measure was much less common. They have a relative risk reduction that's similar to an OPTIMIZE, but actually the absolute risks are very different. This is why it's important to consider the difference between absolute and relative risks. And lots of journals, when you're publishing, will actually ask you to present your absolute risks as well as your relative risks. Investigators sometimes choose to present relative risk because often you can present more impressive results. You can say, I got a 25% relative risk reduction, but actually your change in absolute risks might be very small, and it's really the absolute risk which determines that clinical significance. So in the POISE trial, They came up with a sample size calculation of 4,000 patients per group, a really large trial, to demonstrate that very small change in absolute risk. So their results were, based on that sample size of 8-ish thousand patients, they found an absolute risk reduction of 1.1%, relative risk of 16%, so same absolute risk as the optimized trial, but they demonstrated a significant change, and so their p-value for that was 0.04, which came under that arbitrary threshold, and so therefore they can say the intervention reduces the incidence of the outcome. So we have two trials that demonstrate similar changes in relative risk that had prospective sample size calculations, but actually those results were interpreted differently because of the results of that hypothesis test, that there's a difference from the null hypothesis. So this is a London bus stop. I think that designing trials and doing research is much like waiting for a bus. I'm not mad. And in my experience, I think I'm thinking about a bus stop that's very near me, and I'm waiting for a bus to go into London. I live in North London, and there's maybe 5 or 6 bus routes on this bus stop, and I can just wait at the bus stop, but I can get on the first bus that I want. And if I get on the first bus, it'll probably take me to the general direction that I want to go. But if I get on the wrong bus and I don't wait for the right one, it's not going to take me to the exact destination. And I think you can draw a parallel with research. You can be quite fast in your planning and just crack on with the research and do it and probably go in the correct direction. But if you don't actually wait and plan and go through all the steps that we have mentioned, you're probably not going to reach the destination which, in terms of research, is answering your research question. We mentioned yesterday when we were talking about papers that quite often authors won't actually clearly define their research question. And if you as a researcher don't know what your research question is, it's not surprising then when you get to the end and you're not sure how to answer that question. So the first point from this trial design lecture is really have a key idea of what you're trying to do with your research, what question you're trying to answer, because all the rest of your methods hang on to that research question. Now the research question might be, I'm interested to see what happens if I'm going to generate a hypothesis by just sort of in the lab seeing what happens, and that's absolutely fine, but you've got that idea in the first place. But if you're just doing something to see what happens, you have to have a plan about how you're going to analyse results as well. So taking a step across to clinical studies, I often come across people who say, oh, let's just do this to see what happens. But actually, then when you try and do the statistics afterwards, if you haven't correctly planned and done the sample size calculation, which a reviewer is probably going to ask for, then you'll find it very difficult when it comes to your stats because you probably won't have enough patients, or you have no idea whether or not you have enough patients. Does that make some sort of sense? Yeah. So, number 1, have a clear idea of what your research question is. Number 2, choose the appropriate study to do that. So, going back to the lecture yesterday, thinking about our pyramid of hierarchical evidence-based medicine study designs with our meta-analyses at the pinnacle and our consensus opinion and case reports at the base. Really, if you're trying to answer a question with a prospective study, you're sort of looking for a study design somewhere in the A and B area. So we're sort of thinking about prospective cohort studies, case control studies, or randomized control trials. And of course, as I think it's either this gentleman here or this gentleman here asked yesterday about qualitative research methods, this clearly doesn't encompass that. So think about your exposure and think about your outcome. What are you trying to measure as the effect? Your exposure, what are you interested in that might have an influence on that outcome? If you have a rare outcome, so let's say a genetic disease where there's only a very small incidence in the general population, if you have a cohort study, So you're collecting patients and enrolling those patients as you go along, and you're waiting to see if they have the outcome, and you're studying a rare exposure, a rare outcome, you're going to need to collect a large number of patients to acquire enough patients at the end with that outcome in order to be able to do any meaningful statistics. So that is both time consuming, requires a lot of resources, and will therefore incur a lot of expense, probably take a really long time to achieve. So perhaps if you're studying a rare outcome, you want to opt for a case control approach, whereby you enroll patients that have that outcome measure and then work backwards from there. It might be that you want to determine the effect of a particular intervention, and as we mentioned yesterday, the best way to do that is with a randomized control trial. With a randomized control trial, you are randomly assigning your intervention to patients, so that the two groups, the intervention group and the control group, the only difference between those two groups will be whether or not they had the intervention, and you're assigning that by chance. So you have to do that in a prospective way. So this is going back to the optimized trial now. So somebody was asking about meta-analyses earlier. So this is an example of a meta-analysis. Rupert Pearce and colleagues, when they presented their paper of the optimized trial, they presented data from a randomized controlled trial. But they also, which is unusual, presented a meta-analysis in the same paper. And so they were combining two types of study design from this pyramid. And this is from the SIGN group, as I mentioned yesterday. So here we have all of the studies, and this is an example of a forest plot, which shows the effect size for lots of different trials, and then it aggregates that effect size to show a general effect across all of those studies. And in the optimized paper, they presented this along with their main results, and you can see that whilst in the optimized trial it didn't quite reach statistical significance, when you consider that in the context of all the other trials in this area, the diamond is just away from the line and probably does demonstrate an effect. So this is a really nice, I think, way to show the value of meta-analysis. Particularly for studies that aren't quite big enough to demonstrate an effect on their own. If you take it into the context of lots of other studies, sometimes there might be an effect. This also illustrates the importance of having comparable outcome measures, because if you're trying to do a meta-analysis of this size, there's lots of studies involved. If you can't accurately compare those outcome measures, then it's very difficult to do a valid meta-analysis. So my next tip, so we've spoken about having an idea about your research question, that's key. Thinking about your study design, and that really is based on what outcome you're studying, what exposure you're studying, whether you're allocating that exposure or whether you're enrolling patients in a prospective cohort and just seeing who has that exposure. The next thing to think about is your outcome, because your outcome will determine how big your study needs to be, broadly speaking. So these are primary colours for your primary outcome. And we can think about lots of different types of primary outcome. We were talking yesterday about a study that we're doing, which is a trial of CPAP.
Can I just turn your microphone? It's
you can do whatever you like to do.
Okay, thank you. Thank you. For some reason it's picking up. Not clear why that is. Can I just check the...
You can check whatever you like, it's in my pocket.
Thank you.
Sorry, I'm not used to being filmed, so many apologies.
It all seems to be fine. I'll just...
Yeah, if you want to, I'll just stick it back in my pocket, thanks.
Great.
So primary outcomes, so we can think about like a trial I was mentioning yesterday. So we're doing a trial of continuous positive airways pressure at the moment, and our outcome measure is a composite. It's a composite of reintubation, pneumonia and death. But you might want to choose a single outcome measure, and there are pros and cons of doing those things. But it's really key to have a clear idea of what your outcome measure is. And it's really key to have a clear idea of how to define it. It might be that you're using a group of many investigators. So you're running a study in a single centre, and there's a group of you who are trying to answer a question, and you're splitting the data collection between you. if each of you has a different idea of how to define that outcome measure, you're going to have odd results because you can't be sure that what one person thinks reaches the outcome is what another investigator thinks is an outcome. You're going to introduce a lot of bias there in the way that you interpret your results. Equally, if you're running a multi-centre study where you've got several hospitals, and the way that one hospital defines, let's say, pneumonia is different to a different hospital defining pneumonia, then you're going to have either higher or lower rates in a different hospital depending on how they define the outcome measures. So it's really important to have a key idea of how you're defining that outcome and what is the primary outcome. Often with studies or trials, you will have a primary outcome and then you'll have a series of secondary outcome measures. The primary outcome measure is the main outcome, so it's the main thing you're interested in. And when you're performing a sample size calculation, that's the outcome that you want to take into consideration. Okay. So we spoke about standard outcome measures yesterday, and I showed you an initiative for defining core outcome measures in perioperative medicine, there was this paper by Jammer and colleagues looking at defining core outcome measures in anaesthesia and critical care. And as I said yesterday, this is a really interesting paper. If you're thinking about how to design studies, I would encourage you to use a clearly defined outcome measure with a clear definition that's comparable across other studies as well. So, how do we calculate our sample size? This is quite important for your exercise this afternoon, where you're going to be presenting a pitch for funding and designing a trial. So what's the point of sample size? Well, you want to have a sample that's large enough to be able to do your statistics, to give an appropriate result. And what that means is that you're collecting data from enough patients or samples to actually detect a result if one exists. So essentially we're defining how hard we're going to look for this result. So in general terms, if you have a large sample, if there is an effect, you're going to see a narrower confidence interval, so you're going to be able to estimate your effect size with increased precision. There's two approaches, broadly speaking, to calculating sample sizes. You're either trying to estimate a measure with a specified precision, so you're defining that precision, or you're basing your sample size calculation on a hypothesis test of whether or not you're going to reject the null hypothesis, and you're pre-specifying that significance level. Now, usually that significance level will be 5%, 0.05, but sometimes some people like to specify an even lower significance level, so let's say 0.01, and that's, I think, more common with genetic studies, although I don't have a lot of experience with those. So before we think about sample size, we need to think about error, and this can often be quite confusing, so forgive me if I go through it in a bit of detail. So there are two types of error, broadly speaking. You have type 1 and type 2 error. So your type 1 error is the probability of rejecting your null hypothesis when it is true. So let's just go through that again. So your null hypothesis is usually that there is no effect, and we're talking about the probability of rejecting that. Okay, so we're saying that in this situation the null hypothesis is true, so that means there's no effect. And so your type 1 error is the probability that you reject that null hypothesis when it is true. Your type 2 error is the opposite, really. So it's the probability of not rejecting that null hypothesis when it is false. So in that situation, the null hypothesis is false, i.e. there is an effect. So the type 1 error is the probability of rejecting that when it's true, and your type 2 error is essentially how hard you look for it. Let's just have an example of that because it's quite confusing. So I don't know if you've seen this meme. This is something that goes around on Twitter. I've seen it loads and loads of times. So in this situation, your null hypothesis is that there is no pregnancy. And on the left-hand panel, we have our type 1 error. So we are not rejecting our null hypothesis, and we're saying this guy is pregnant when actually he's not pregnant. And the type 2 error is saying that you're not pregnant when actually you are pregnant, because clearly on the right-hand side, the null hypothesis of no effect is false. Why is this important in terms of power? Well, power is directly related to your type 2 error. So remember, type 2 error is essentially how hard you're looking. Power is 1 minus your type 2 error. And usually when you're doing sample size calculations, the power that we generally expect is 80%, although some people like to increase that power to 90%. And so that has a key influence on sample size because it's how hard you're looking. So let's think about calculating a sample size for a hypothesis test. So the most common hypothesis is going to be a t-test. And we are stating our null hypothesis of no effect, and we're looking to see whether or not that is true. These are the things that you need for a hypothesis test. So you want to know how common your outcome is in one group, and usually we look at the outcome, the proportion in the control group. So let's say we're interested in the incidence of pneumonia in patients that are having major surgery. So the incidence of pneumonia in most patients having major abdominal surgery, let's say over 50 years having open surgery, the incidence of pneumonia is probably about 8%, 8 to 10%. Okay. We also want to know the minimum between group difference that we're interested in. So back in the optimized trial, we saw that there was a 16% relative risk reduction. It's the same as POISE. So their sample size was worked out on a presumed relative risk reduction of 25%. So we're looking for a between group difference in the incidence of pneumonia, in this case of 25%. So we're looking for an absolute risk reduction of 2%. Yeah. We're interested in the power, so how hard we're going to look for this, of 80%. And we're predefining our significance level, our type 1 error, as 5%, and that's usually standard. So if you look through all of these, pretty much of it is always going to be standard. We're probably always going to start off with a power of 80%. We're probably always going to start off with a type 1 error of 5%. So really, the top one is the key thing, because you need to know what you're expecting the instance of your outcome to be before you start. And that can be achieved in two ways. You have to have done a thorough literature review to know how common your outcome measure is. In the laboratory, it might be that you've done some preliminary experiments to find out what's going on, so that can facilitate your sample size. If it's something that's completely new, you might need to do a feasibility study where or a pilot study to define the incidence of the outcome before you can then go on and define a proper sample size calculation. And then you want to think about how reasonable you think a change in that outcome measure is according to the intervention you're proposing. So the top two things are really the only things that you can vary to begin with. But it might be that then you get a sample size that's unrealistic, and so you might then want to vary some of the parameters to see how that changes the sample size, and that's completely acceptable, and that's generally what you do. So you start off with one set of parameters, and then you'll change it slightly to see how it affects. Sample size calculations are a malleable process and iterative, and often it changes until you get something that you think is feasible for you, because sample size will be the biggest determinant of cost and feasibility for your study. There are many ways to calculate sample size, and I'm not going to go through all these because the mathematics can be quite complicated. This is just an example of some of the maths that you might want to do for a sample size. I don't understand this algebra. It's from Wikipedia, but I don't understand it. This is where I would look if I was doing a sample size calculation. It's this book, which is one that Hugh recommended. It's Kirkwood and Stern, this has a really good section about sample size calculations, and it goes through 9 or 10 different types of sample size calculation for different types of study. So the key point to remember about this is that there will be different ways to calculate sample size based on the statistic that you want to use. So you can't just apply the sample size calculation from one set of planned analyses to another, because they're not comparable, and your numbers will change based on what statistical technique you want to use. So going right back to the beginning of the talk, you need to plan what you're going to do before you do it, because your planned statistical approach will definitely influence your sample size calculation. Okay, so going back to the 2 slides before when I was talking about the different sample size approaches for a hypothesis test versus a precision estimate, those two will have 2 different types of approach in terms of the sample size. In practice, how would I do a sample size calculation? Well, I would use a statistical package, and this is a screenshot from Stata, which is a really commonly used statistical package. Stata is really excellent because it has a whole set of functions for calculating sample size. So here you can see that you can set your significance level, and this is a sample size calculation for comparing 2 proportions. So let's say the proportion of patients with pneumonia in one group compared to the other. So we're setting our type 1 error level, our significance, which is 0.05. We can define the ratio of allocation between 2 groups, which will be 1 to 1. And then we can define the expected proportions in our group. So we'll know what our control group is because we've got previous evidence. We can say that in previous cohort studies, the incidence of pneumonia was 8%. And then we can then work out what we think that our effect size is going to be in the intervention group. So let's say we wanted to type 25% relative risk reduction. So we've got 8% in here, 6% in here, and we can then calculate our sample size calculation. You can also use online calculators, and these are really helpful if you don't have the use of a statistical package like Stata, which can be quite expensive. These are really good as well. This is an example that you could use that I just found on Google. And you might want to take note of this for later on when you have to do a sample size calculation for the group work later. It's the same boxes, the same questions that it's asking, and on this particular one at the bottom of the page, it will give you a series of estimates based on different values around the limits that you put in. So it will say, if you change the power to 90, how much will it increase your sample by? If you change the relative risk parameters by a little bit, or the proportion parameters a little bit, how much will it change your sample size? And that's the sort of fine-tuning that you're doing. The other way that you can fine-tune your sample size calculation is by thinking about your primary outcome. So the primary outcome, remember, is the outcome measure that you're powering your study on. Do you choose a single outcome measure or do you choose a composite outcome measure? What are the benefits of doing that? Well, the benefits of a composite outcome in this case are that it's probably going to give you an increased number of cases that are going to meet the primary outcome. Because if you include more diseases within the outcome measure, more people are probably going to achieve them. So let's take the example again of that CPAP study. So we could have said in our CPAP study, we're just going to choose pneumonia as the outcome measure. So we know that the incidence of pneumonia is about 8%. Well, that's great. But actually, if we use an incidence of 8% for our sample size calculation, the sample size is going to be far too big for us to do feasibly. It's going to be too expensive. We'll have to include too many centres and too many patients, and it will take too long for us to do. And we're talking maybe like 6, 7, 8,000 patients, so really big. If we also include patients that are reintubated or die within that time period, that's going to increase the number of patients that meet that outcome up to, let's say, 12 or 15%. And that then means that our sample size calculation is going to be that much smaller because we're having more patients as a proportion reaching that outcome measure. So here's an example of a composite outcome measure. This is a study that Hugh and I did a few years ago. This was a cohort study looking at the National Early Warning Score, which is a warning score used on most hospital wards. It's a composite scoring system that includes values such as heart rate and blood pressure and respiratory rate and temperature, and it comes out with a score at the bottom which essentially says how well or unwell is a patient. And we were interested to see whether or not this new early warning score, the National Early Warning Score, or NEWS, whether that was effective at predicting short-term outcomes for patients in hospital. And we chose a composite outcome measure of critical care unit admission from a general hospital ward, or if the patient died. And if we had used either one of those outcomes as that composite, so either critical care unit admission or death, we would have had to have increased our sample size to make sure that we got enough patients meeting that primary outcome measure. But we used a composite outcome, which meant that we could have a smaller sample, and that was to do with reasons of feasibility. We ended up recruiting about 400 or 450 patients into this study, but if we had had single outcome measures, we would have needed to collect about 600 or 700 patients, and so that made the study for us easier to do. And these are the decisions that you as investigators need to make, because you can have an idea in your head about how you really want to do research and do it to the perfect level in the perfect set of situations, but actually in reality the real world isn't perfect, and you have to make compromises but still maintain the integrity of the study, and the way to do that is to do things in a planned and coordinated way, in my opinion. So we're now thinking about trial design. I'm relying heavily on our CPAP study because this is one that's fresh in my mind at the moment. We're going through a series of initiation visits at the moment to bring new sites online for this study. It's a multi-centre study, as I said yesterday, and in the UK we're recruiting between 15 and 20 hospital sites. So this is a slide from that initiation visit presentation, and this shows the timeline for our study. And this is analogous in a way to that Gantt chart that Anne was presenting yesterday about how you would run a study across the whole duration of the study, but this takes it from a patient perspective, as in the patient going through the trial. And this is what you would want to sort of have planned out in your head when you're thinking about how you're going to run that trial. So I'll just take you through this as an example. Here we have the before surgery situation where we're identifying patients and we're saying, would you like to take part in our trial? And you have to think about where you're going to identify those patients from. If you're doing a pharma trial, it might be that you're approaching patients in a clinic. Let's say we're looking at an intervention of a blood pressure reduction therapy. We might be approaching patients in the GP surgery or the general medical clinic to see if they have high blood pressure and would they like to take part in your trial. In our trial, we're seeing if patients would like to take part when they come for their pre-assessment visit before they have an operation. We're giving them patient information sheets, and we're explaining to them about the trial, and we're giving them an opportunity to go away and think about the trial before consenting to take part. When they come in on the day of surgery or before then, we're asking them to sign a consent form, and it will vary a little bit on where the hospital is and how they're set up as to whether they'll do the consent in the time between their pre-assessment visit and the surgery, or whether they'll do it on the day of surgery. And then in this study, we're then randomising the patients at that point to whether they receive the intervention or usual care at that point. They would then have their operation. And after their operation, if they're in the intervention group, they will receive the intervention, which is the continuous positive airways pressure. After that intervention period is over, we'll then begin our follow-up procedures, and often for these surgical trials there's a pretty standard follow-up, which involves reviewing the medical notes, speaking to the patient, perhaps looking at blood results and those sorts of things to get information about how well or unwell the patient is after their operation. And after that follow-up is complete in hospital and the patient has gone home, in this trial we're then giving the patients a telephone call after 30 days to see how they're doing, to see if they've had any medical complications between the point of hospital discharge and that 30-day point. And in this trial we're also looking at 1-year outcomes. And the reason for looking at 1-year outcomes is interesting because our primary outcome measure is at 30 days. And this is really common for surgical trials. We're looking at a period of between the operation or the intervention and the 30-day point. And that's seen as a relatively reasonable time period to assess post-operative complications. But actually it's sort of counterintuitive, because if you're a patient and you're having a surgery, from your perspective, from my perspective, if I was a patient, I would definitely expect to be alive 30 days after my procedure. I'm really more concerned about how well I'm going to be for the rest of my life. And so the fact that we're assessing in general, this is not just this trial, this is lots of other trials as well, that we're assessing our main outcome measure at 30 days is slightly odd. And so for this trial we're also looking at 1-year outcomes. And I think there's a general move to looking at much longer term outcomes as we realise that the impact of major surgery actually has a really long-term effect. And if you get any complication within 30 days of your procedure, we know that it has a really long-term impact on patients' function. So there's a really famous set of slides by an investigator called Curie, who showed that any complication after the operation within 30 days will have an impact on long-term survival, and there's a clear difference between patients that had a complication and patients that didn't have a complication, and I think we need to be focusing on much longer-term outcomes. However, that being said, it has really big impact on the feasibility of the study. So you're running a multi-centre trial and you're doing follow-up to, say, 5 years. That's going to be really hard because you have to have infrastructure for 5 years. It makes the project really long. Staff costs will be high. You're not going to be able to publish the results for a really long time, which means that actually a dissemination of those results is prolonged for a long period of time. And probably you're going to have a dropout rate. And that's something that people forget, is that actually when you're ringing people up, they might have moved house, they might have changed their phone number, and if you can't contact these patients, it has an impact on selection and introduces selection bias into the way that you interpret the results. So these are all things that you need to consider. In this trial, we decided to go for 30 days because that was really standard, but I think we're thinking about, in the future, as things progress, perhaps changing to 180 days or longer. So this slide has come up quite a lot over the last 2 days, but I think it comes up because it's really important. So look at the standardised reporting requirements and make sure that on your checklist for whatever study you're doing, whether it's the STROBE guidelines for your consort, your STROBE guidelines for your cohort study, or your consort guidelines for your randomised control trial, or your PRISMA guidelines for your meta-analysis. Have a look and see what's on that checklist before you do the research, when you're planning it, to make sure that you're ticking off all the boxes, so that when you come to write it up, you're not going to have a missing line on your checklist because you haven't done it, and you can't go back in retrospect and answer that. Because, as I said yesterday, a lot of the journals now are asking you to fill out these checklists against the standard reporting requirements to see whether or not you've done it. And the reviewers may well ask you, why didn't you do this, why didn't you do that? And it's much better to think about these things beforehand so you can plan, rather than having to justify why you didn't do something out of error or not thinking through things to begin with. In my opinion, it's much better to plan ahead and think carefully before you do things. We also spoke about trial registration, and this is a screenshot from a trial registry called ISR-CTN, and this is run by Biomed Central, which is a group of journals that are, I'm pretty sure they're now mainly open access journals, actually, the Biomed Central journals. So this is just an example of a registry where you can register your trial. ISR-CTN are good because they register studies that aren't just trials. So quite a few of the trial registries are just for randomised control trials, but ISR-CTN will register other types of study, whether it's a cohort study or a case control study. And that's really good because you can prospectively lay out what your methods are and what your analysis is going to be beforehand, and then a reviewer or a reader can then go back and compare to what you planned to actually what you did. Another example is clinicaltrials.gov, but that is more focused on clinical trials. The difference between these two are the cost. So clinicaltrials.gov is free, whereas ISR-CTN has a cost attached to it. So that's another thing to think about. I would definitely recommend that you register your trial if you're thinking about doing one. Because if you don't register your trial, you probably won't get published. But I think there's a move now to registering all types of studies as a gold standard. So when you're preparing your study later, and you're planning how you're going to conduct your research, and you're standing up here where I am presenting to the group about why we should fund you, I really think you should refer back to your PICO. This is an excellent way to present your plan in terms of the key components of the study: the population, the intervention, the comparator, and the outcome. So have this in your head when you're discussing things later on, and it will act as a framework for you to hang things on. So what are my top tips? Think about your intervention, think about your primary outcome, and do your sample size targeted towards that. If you're going to be running a trial, and particularly if you're going to be applying for public money in this country, it's best to involve a clinical trials unit. And there are a series of accredited clinical trials units in this country. There's about 30 of them, and they have infrastructure and resources to be able to run every aspect of your clinical trial, from trial management, statistics, database management, governance, records, all of these types of things. They will all be in one place, and that's why a clinical trials unit is really good. And it gives the funder a reassurance that you're going to be running your study with a level of expertise and experience. And what the funders are worried about is that they're going to give you a substantial amount of money, and they really want you to deliver on what you're promising. And going to experts in delivering trials is a really good way of demonstrating that you're going to be a serious candidate, and that you're likely to complete what you're setting out to do. If you're applying for money from the NIHR, for example, it's likely that your application wouldn't even be looked at unless you had a clinical trials unit involved. In the same vein, even if you're doing a small study, an observational study, a cohort study, think about what statistical expertise you're going to use and try and get them involved early. This can be really hard because sometimes it can be difficult to involve or find a statistician, but it's really important to think about your statistics beforehand, because that will impact on so much as you go through the study. You don't want to be in the position where you get to the end and you've done your analysis, and then the question that you get from the reviewers is, what was your power calculation? What did you power your study on? That should be something that you're thinking about right at the beginning rather than right at the end in a retrospective way. Hugh already mentioned the Research Design Service, but this is an NIHR funded service, particularly in London. It's a really good way of getting free advice about how to design your study. And if you're struggling to find a statistician, often lots of Stats MSc courses will require projects for these students to do, and so perhaps you could tap into that resource to have some free statistical input. That's something to think about if you're looking for a statistician.